is the ionization enthalpy? Ionization enthalpy means amount of energy required to remove the electron from the gaseous atom. Clear? That is called ionization enthalpy. We'll discuss the facts related to d block elements. In mainly we will focus on the 3D series. Clear? We want to discuss 3D, 4D, 5D. So some general facts are there. Whenever the loss of electron gives the stable electronic configuration. Stable electronic configuration means whenever D subshell contains either D5 or D10 configuration, that is comparatively more stable as compared to any other configuration of D subshell, means whenever loss of electron will give D5 or D10 configuration, then it would be easy. Clear? Means ionization enthalpy will be less. Clear? But whenever electron has to be removed from the D5 or D10 configuration, then it will be very difficult for the atom, means ionization enthalpy is very high. For example, if we see the example of 3D series, cadmium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Clear? We are discussing here the second ionization enthalpy. Energy required to remove the first electron from the atom is called first ionization enthalpy, second electron, second ionization enthalpy, third ionization enthalpy. Clear? So we are discussing here the second ionization enthalpy, for example. So if we move from left to right in the periodic table for 3D series, if we take the example of chromium to manganese or copper to zinc, what is the general trend of ionization enthalpy on moving along the period? Size decreases when we move from left to right because nuclear charge increases. So due to increase in nuclear charge, size decreases. Is a general fact in any of the period. So size decreases. It is very difficult to remove the electron from the small atom. So what is the general fact? Ionization enthalpy increases on moving from left to right. Clear? But there is a drop in ionization enthalpy, means it is decreases when we move from copper to. For rest of the element, the general fact is size decreases on moving along the period. In ionization enthalpy decreases. Clear? But ionization enthalpy increases. But there is a drop in ionization enthalpy, second ionization enthalpy, when we move from copper to manganese or from copper to zinc. The reason is here, clear? Because the second electron has to be removed from the stable configuration. Here is from D5, clear? And here is from D10, clear? Hopefully you are aware with the electronic configuration of these elements. Electronic configuration is D10. Clear? So this time there is a drop in the ionization enthalpy because the electronic after the loss of the second electron, the configuration becomes D10. After the loss of the two electrons, it becomes, the configuration is D5 4s2. Clear? So after loss of two electrons, it becomes D5. After loss of two electrons, it becomes D10. So it is very easy for the atom to lose two electrons for zinc and manganese. Clear? Similarly, we can predict the ionization enthalpy of manganese or iron as well. Here we will discuss the third ionization enthalpy. In the similar grounds, we can predict the ionization enthalpy whether third loss of third electron will give the stable configuration or electron has to be removed from the stable electronic configuration. Clear? That will decide the third ionization enthalpy of manganese or iron. Clear? What is the electronic configuration of manganese? 3d5 4s2. So loss of second electron gives the stable configuration, means second ionization enthalpy is very less. But loss of third electron will take place from the stable configuration, means after loss of third electron it becomes unstable. So third ionization enthalpy of manganese is very high. Clear? But if we take the example of iron, it has the configuration 3d6 OH2. Clear? So what is the third addition enthalpy for iron? Is less or high? Comparatively less. After loss of third electron, it becomes stable, means the configuration becomes 3d5. So third addition enthalpy of iron is very less, whereas manganese has very high. This is a common ground. Clear? This will be followed in each of the series of the transition elements. I repeat again, whenever electron has to be removed from the stable electronic configuration, then ionization enthalpy is very high. Whenever loss of electron makes this type of stable configuration, then ionization enthalpy is very less. Clear? One more common fact is there for first ionization enthalpy. First, the trend of the first ionization enthalpy is not regular for the 3D series. What is the common expectation in the 3D series on moving along the period? Ionization enthalpy should be increases because size decreases regularly, but you will see many times increase and decrease in 3D in the as far as the first ionization enthalpy is concerned. What is the reason behind this? As you know, electrons are filled in the penultimate shell, not the valence shell but penultimate shell. So whenever electron is removed from the penultimate shell or sometimes from the valence shell, it will reorganizes the energy between the valence shell and penultimate shell. Clear? That's why there is a irregularities in the first ionization enthalpy or moving along the period. Clear? You will get this question in the exercise as well, that why the trend of first ionization enthalpy for transition element is not regular. Clear? This is because electrons has to be removed from two shells. Generally, in S block element and P block element, electrons are removed from the valence shell only. Clear? So reorganization of energy between different shells is not required to be occur. But in this case, electrons are removed from the two different shells, valence and penultimate shell. So whenever electron is removed from any of these two shells, there is a reorganization, rearrangement of energies between these two. That's why a regular trend will not be observed in case of first ionization enthalpy for 3D series. Clear? So this is all about the ionization enthalpy of D block elements. Clear? Next is the magnetic properties. Mainly two different magnetic behaviors are observed in case of transition elements. One is the diamagnetic, second is paramagnetic. Okay. Occasionally, ferromagnetism is also discussed. Ferromagnetism. But we have to confine in these two type of magnetic behavior, diamagnetic and paramagnetic. Paramagnetic behavior will be observed when one or more unpaired electrons are there in the orbital. Clear? Whenever one or more unpaired electron is there in the atom, then its behavior is paramagnetic. When all the electrons are paired, then it is diamagnetic. In more the number of unpaired electron, more is the paramagnetic behavior. What is meant by paramagnetism or diamagnetism? Suppose if I say this is a paramagnetic substance or paramagnetic element, it means whenever suppose this is the external magnetic field, this is a magnet. Clear? So whenever a magnet will come near the paramagnetic substance, there is a weak attraction between these two. So that type of substances which are attracted weakly towards the external magnetic field or applied magnetic field, they are called paramagnetic. And if weak repulsion occurs between the substance and external magnetic field or applied magnetic field, that is called diamagnetic. So here you can understand easily the reason behind the diamagnetism or paramagnetism. The extreme case of paramagnetism is called ferromagnetism. Clear? When large number of unpaired electrons are present in the atom, then there is a strong attraction between the external magnetic field in the substance used. That is called ferromagnetism. Means ferromagnetism is the extreme case of paramagnetism. Clear? One more thing you have to do here. You have to calculate the magnetic moment of the elements. Clear? So magnetic moment can be calculated with the help of magnetic moments are calculated in case of paramagnetic substances only. Clear? In case of diamagnetic substances, magnetic moment is zero. Clear? Because all the electrons are paired, so magnetic moment is partially cancelled by each other. Clear? So net magnetic moment of diamagnetic substances is always zero. In magnetic moment can be calculated. It is denoted by mu. In calculated with the help of under root n plus 2. Clear? Where n is the number of unpaired electrons. So how many unpaired electrons are possible in D subshell? Either 1, 2, 3, 4, 5. 1, 2, 3, 4 or 5. Clear? More than 5 is not possible because after that pairing will start. Clear? So minimum number of unpaired electrons can be 1 and maximum it will be 5. If all the electrons are paired, means n is equal 0. Clear? That is the case of diamagnetic. So if you put 0 here, then magnetic moment will be 0. That is the reason diamagnetic substances have 0 magnetic moment. Its unit is Dm over magneton. Clear? Over magneton is the unit of magnetic moment. Clear? So we have to calculate here the magnetic moment of paramagnetic substances for 1, 2, 3, 4 or 5. Clear? 1, 2, 3, 4 or 5 electrons. This could be the value of n. Clear? Clear? So if you put 1 here, clear? You put 1 here, what value will come? You can remember also, or you can calculate under root 3. So 1.7. Over magneton, it is, you can remember it also because it is used in the NCERT numericals, NCERT questions and unit exercise. It is very easy. 1, 2, 3, 4, 5. First you have to remember that whenever the unpaired electrons are 1, 2, 3, 4, 5, their magnetic moment will come 1 point something, 2 point something, 3 point something, 4 point something or 5 point something. Then there is an increasing number. Clear? 7, 3, 8, 4, 8, 7, 9, 0, 9, 2. Clear? If you remember these values, you don't need to calculate this. If you don't like this, then you can calculate in the paper. If you feel that sir is saying that you have to remember the values, रटने के लिए बोल रहे हैं, then you can calculate also to get the same value. Clear? So these are the magnetic moments of paramagnetic substances. In case of diamagnetic substances, it is zero. Clear? So here, so far we have discussed two properties today.